Hi, I would like to start off this presentation by having all of you quickly imagine a scenario. You're sitting in your hotel room with an outlook on the setting sun. It's getting a little bit cold outside, so you had a window open, but now you close it, and you get inspired. So you make yourself a cup of hot tea, and you get a laptop, you put it on the table, and then you just decide to just copy the scene one-to-one into Blender. So you get all of your models, textures, what have you, you make all the shaders, you press F12, and then something doesn't look quite right. I think the first thing that you might point towards is probably an issue with your lighting or color management or something like that. But this time, no, it's something else entirely. So first off, the intensity of the reflection on the table of your laptop screen just doesn't match. Even though you've looked up the correct IOR values in whatever your database of choice is for that, it still doesn't quite match. The atmosphere looks slightly different, and I think most curiously, the sun is gone. So today, we will be taking a look at where the traditional models used in Blender fail. So, and Blender crashed. Great start. Wrong Blender? Right, wrong Blender. Reopen. Okay. Let's try that again. Okay. So we will be talking. I already said that actually. Okay, next slide. Actually, no. Okay, so physics is a complicated topic. It's no surprise to anyone. And reality converges poorly. We need results quickly, ideally interactively, and we need it to work most of the time. And just like this, most of the models that we use, like ray optics, came to be. Okay, so I would my first demo here is actually of a phenomenon which exists in a lot of real-world scenarios, and it exists in the atmosphere, which is why that sun from before was gone. Because as the sun just barely touches the horizon, when we see it that way, it actually is already behind the horizon. And the large length of space that it goes through a gradient index of refraction media causes it to appear as if it was still there. And this is actually pretty simple to demonstrate. Actually, I could probably take my phone and actually show it. Okay. So as you can see, the laser beam is visibly sagging downwards. This happens primarily because we have a gradient in the concentration of sugar in this water. This is just sugar, water, and a little bit of cream to scatter the light so we can actually see the path of the ray. Okay. So the big question is, how do we model this? The proper approach would be to essentially just ray march, and then just bend. Unfortunately, that is hard. That requires us to make a render that supports that, and it's pretty expensive to calculate everything this way. And the simplest thing we can do to sort of hack it into something like cycles is to essentially just take an approach similar to surflets, where we essentially just stack a bunch of layers of certain index of refraction, and each new layer sort of increases, essentially just increases the refraction. So this works. This is how it looks like. This is the scene without, and this is with. I had to increase the light paths a lot, and also light tree is getting a bit messed up, but this is a functional solution. So what are some improvements? First of all, orienting it towards the camera. I have sidestepped doing that entirely, so when we look at it sideways, we obviously see the holes between the sort of layers. So see holes. And the next approach is probably to do something like jitter the exact location or something like that to avoid getting banding in the most general case. It's not really visible. Maybe it won't be an issue. It's potential improvements. Okay, so let's look at some more examples where we can see this gradient. So we see mirages, not the map, mirages. The change in temperature causes this pseudo-refraction reflection event. So essentially, a light eventually goes, if we look down, it refracts sort of bending like straight, and we see essentially a reflection event happening there. So the next example would be that cup of tea, which is pretty much what I was emulating there. We actually have a set of gradients there. We have a temperature gradient. The higher the temperature is, the lower the index of refraction. We have a concentration gradient of sugar and the actual tea. So all of those change the index of refraction. Properly simulating it is pretty important. And lastly, I would like to talk about the fact that all light that you currently see actually goes through a medium with a varying IOR. And I'm talking about your eye lenses. Because our eyes need to be relatively compact and they got to do their job of focusing light down and still have to be pretty small, the cool evolutionary trick that just happened to happen is that our eyes, the lenses in our eyes actually have a different index of refraction depending on where exactly we're trying to measure it. Okay, so next. Okay, so a model that we commonly use is that the refraction depends on a handful of factors. It depends on the angle of incidence, Snell's law, and the medium, or essentially how strong, which controls how strong the effect will be. So it's actually a bit more complicated than that. So first off, okay, give me a sec. Okay, you know what, we're just going to skip that. I'm probably going to spend more time thinking about what I was supposed to say here than actually doing it. Okay. Okay. So, real quick, let's take a look at polarization. Now, polarization is actually very important. It controls a lot of things. One very common model that you've probably at least heard of if you were developing any renderer is the Schlick approximation. It's pretty universal. And essentially, in the real world, the specular, the intensity of specular as a function of the angle, there are actually two paths depending on which polarization we consider. Now, in practice, a lot of lights that we see are roughly equally polarized in all directions. So essentially what the Schlick approximation does is it just fits a polynomial between these two lines. And that works fine for non-polarized lights. Okay? It's going to be very scuffed. Hold on. So this is just a piece of acrylic. This isn't... Oh, hello. Okay. This is nothing special. Okay, why is it lagging? Okay. So as we can see, if we, depending on the exact angle that we okay, what is going on? Depending on the angle that the polarized light is hitting it, we get different intensity in our reflection. We also get a different color. I'm not 100% sure why we get that. This happens because the laptop screen emits mostly polarized light. And the thing that we're seeing here, if I'm lining up just right, which is pretty hard, we can actually see the intensity dip down to almost 0. Okay, perfect. Next up, we can actually get some really funny effects with a polarization filter. So if I just stuff a polarization filter between the camera and the laptop screen, we get this, well, one, we get weird rainbowing, but most importantly, you can see how it gets significantly darker. Like if I do it like this, compared to when I do it like this, which makes sense. Another cool thing that actually happens is that dielectrics actually tend to flip, no, not flip, rotate the polarization. So if I just put this is regular Scotch tape, nothing special. If I just put it between the screen and the camera, the filter, it actually flips it backwards, which lets us see it more brightly again. So this part is what really poses the challenge, as it's this type of nonlinear behavior that makes it extremely an extremely complicated effect to render. So the approximation here would be just to essentially just hard code some of the stuff into a shader and compute some relative angles. There's a formula you can find for the attenuation that would happen with the light from that. And if we spin it, we can just get this type of attenuation. So I'm going to actually forgot to demonstrate that in the real world. It's a bit hard to see, but yeah, we can simulate some of the simpler cases by just attenuating the light a lot. The problem, once again, is that it's non-linear. Ideally, you would keep track of both paths that polarized light and non-polarized light takes, and you would calculate how they could sort of rotate into each other, and it's a bit of a mess. There are, as far as I'm aware, no commercial renderers that actually do that, and there are especially no renderers that are available to the public that do that. I would like to mention that some of the effects I'll be describing today have been handled and tackled in rendering before, but it's primarily restricted to like really impractical toys, essentially. As far as I'm aware, there are no renderers integrated into a proper pipeline that keep track of polarization. Okay, so let's talk about where polarization matters, because I've just demonstrated a a pretty synthetic case. But there are actually a lot of effects that a lot of places where we can see this effect. The first one is okay. Can you go back a slide, please? Okay. So obviously computer screens, but also the Earth's atmosphere just happens to spin that polarization around, and this is so. If you're just looking at skylight, it's going to be polarized. This is part of the reason why we have things like sunglasses, which are made from polarized filters. We also, if there's any photographers in the audience that had to photograph water, there's also a special. You've probably seen the special lens, which has a polarization filter in it, which is specifically for like outdoor water photography or something like that. It's pretty niche, but it essentially lets you block out a lot of that spectral reflection that the sunlight has. Okay, reflections from dielectrics. The thing, once again, this is just a piece of plastic, acrylic, right? But it's not specific to acrylic. Any dielectric actually exhibits these properties. Okay. Next up, anisotropic materials. So in here, I have a piece of calcite, also called Icelandic spar. And it has a very interesting property of having two different refraction indices for two different types of polarized light. Okay. So as I spin it around, you can see that there are two copies of the text that are shifting relative to each other. Not sure how easy it is to see on the text. Originally, I was supposed to demonstrate it with the same piece of acrylic. The grid might make it a bit more obvious. Just got to straight the camera somehow. Oh, God. It's a pretty obvious effect. Now, the reason why it happens is, once again, anisotropy. And this is actually something that happens in a lot of crystals, this double reflection. You have materials like rubies, sapphires, and even ice. All of those exhibit some degree of this doubled up refraction. And once again, that is polarization. I don't have an intuitive way to think about it, but I think one polarization just it gets slowed down more. There's a higher probability of interaction there. And once again, it also depends on the relative axis of rotation. And right, ice. Let's get back to ice. Where do we see a lot of ice? The atmosphere, of course. Ice is very prevalent in especially higher areas of the atmosphere, levels of the atmosphere. And if you want to render a realistic atmosphere, you might want to have some ice particle simulation going in there. Okay. So next up, we get to some weirder stuff. Okay, I would like to start off with a story. It was some year. I'm not strong in history. And this all takes place in the French Academy of Sciences. And the French Academy of Sciences at the time was holding a competition of some sort of who could explain light behavior the best. And so, one of the participants, you probably heard his name, was, time to butcher some French, Jean-Augustin Fresnel. And he proposed in his paper that light behaves like a wave. And today we know that, yes, light doesn't indeed have some wave-like properties, but back then, nobody really knew about that. And so one of the judges of the competition You've probably also heard their name. They're primarily a mathematician. Um, it was Poisson. I forgot which the rest of his name, but Poisson. You've probably heard of the Poisson disk. It's used as a low discrepancy sequence for anybody that doesn't know. Essentially, he okay, Fresnel in his paper provided some cool math that one could do to simulate some of the light effects. And so what was his name? I already forgot. No, not Fresnel, the other guy. Poisson, thank you. Poisson actually imagined a very simple case where you have a beam of light, a perfectly round, opaque shadow caster, and his super epic math skills yielded him is that if in that case the shadow should have a bright spot in the middle, which is kind of counterintuitive because usually we get those penumbras which essentially we get like gradients outside where a source of light is fully exposed. We get no shadow, then we have a penumbra for when it's only partially exposed, and then we have an umbra where it's completely occluded, and that doesn't really make sense. Okay, so one person did a science, and he actually just ran a test, and he just used a light source. I think it was the sun, and just a ball, and he looked at the shadow, and lo and behold, there was indeed a bright spot in the middle. Now, I should mention that doing this test properly back then was actually a fair bit harder, because back then there were no lasers. But in today's world, we do have lasers, which means I can actually demonstrate this happening, and it might be a little bit hard to see. All right, slow down, gotta slow down. Okay. And do we see anything? Okay, yeah, it's just a blob in my eyes, so I'm just going to try to bring it a bit closer here. Okay, I'm not sure. Once again, it's kind of hard to tell whether or not it's possible to see anything. Do you guys see anything in there? The bright spots? Yep, okay. So why does this happen? Once again, light has wave properties, and this is what we're seeing. The reason why we don't really see it in that often in reality is because this exact effect takes a very specific ratio of the distance from the light source and the shadow caster, and also we're talking about microscopic scales here. Okay. In practice, once again, nobody probably would ever think of simulating this, because simulating this for an entire hemisphere would be painful and extremely noisy, to say the least. So once again, the exact integral, which is used to compute that light spot, you can find it online. It's on the Wikipedia page for Arago spot. Okay, well, skipped over that. And it actually, you can actually just sort of use Blender as a really efficient integral estimator. The problem here is that even though you can compute it analytically, the issue here is that it has a bunch of high-frequency detail, which takes a fair bit of samples to properly converge. But after a little while, we start seeing the shadow, and inside the famous bright spot. Okay, let's talk about objects with small details. Or where do we see objects with small details? The answer is everywhere. Okay. This is why we have roughness as a parameter in like principled or whatever. And the thing is that we don't actually model them. We essentially just model them statistically, which is where the microfacet model comes from. So we simulate interreflection and the roughness as essentially just a purely statistical phenomenon. Okay, there's a probability of light going in a certain direction. Okay, so let's talk about things that where small detail, correctly modeled small detail matters most. CDs, DVDs, and Blu-ray discs. This is one we've probably all seen. That rainbow effect, that's the interaction of small little protrusions and light, thin slices of meat and layered materials, diffraction spikes. We probably, I personally really love the effect. You might know it under the name of glare, the compositor node, that little star-shaped thing. And the more, I personally know it under the name of FFT bloom. Usually that's because that fast Fourier transform is the only way to compute a shaped bloom like that quickly. Corona effects around the sun and moon. Cloud iridescence, this is a very rare effect. I think it's just worth that you look it up if you've never seen it before. And speckle noise, which is actually something that you've seen as I've been trying to show the laser on camera. Our eyes exhibit some of it as well, but it's more obvious on the camera. So this happens because we have a very short wavelength. No, not short. What's the inverse of broad again? Narrow, thank you. A very narrow spectrum, which makes this noise very apparent. It's prevalent in all cameras, eyes, whatever. If there's a small hole, you can probably find some speckle noise in there. Okay, let's talk more about models that we commonly use. So the general assumption behind rendering metals is that metals do not transmit light. I'm going to quickly go into that now. So in dielectrics, you have some light which just reflects specularly, and that is it. And some light that actually goes under the surface and then interreflects and comes back out. So it happens with all dielectrics, at least a little bit. On larger scales, you call that subsurface scattering, what is going on here, but on like smaller scale stuff that you don't really see much of it, it's just the diffuse lobe. So the diffuse lobe just scatters in a very smooth manner around, and the general idea behind metals is that they don't actually have that diffuse component whatsoever. So, when you have a metal, you don't expect it to be transparent, right? But actually, metals have despite having a really high extinction due to the interaction between the light, the metal causing an opposing force, it has a really high extinction, but that really high extinction isn't 100%. So if you block out all of this specular reflection, and you just get this is just like a very thin sheet of gold, you can see straight through it. There's a bluish tint in there as well. I assume it has something to do with that. More of the blue light penetrates through. Anyway, so this is a really baseline assumption. Can we render this in cycles specifically? Yes we can. Just got to real quick find where that is. So maybe gold sheet. No. Well, I can't. I don't think I can actually find it. Find the actual parameter. Ah, there we go. So this is just a shader. So we have, just a regular gold material up close, and as we move closer, I just like lerp it into a more transmissive material. That's all that's happening here. It's not technically physically correct, but it is possible to fake reliably, and it could be, and if you have an entire sort of light blocker around your camera, you can just render it with a regular renderer, but just having a little bit of transmission. Okay, so I'll now try to demonstrate something even weirder. So this, okay, gotta stick it. This is a piece of glass with indium tin oxide on it. It's a composite material, and as you can see, well, you actually really can't see the anything on the piece of glass. But the funny thing is that it actually gives conductivity to this material. And if I just plug that in, so this is just regular just putting 5 volts through it, through a resistor, have an LED, just like that. It lights up, so it's conductive. Okay, so it is used commonly in displays, the ones in your laptop, sometimes, aircraft cockpit windows, architectural glass. I guess it might be useful for rendering this more correctly, might be useful for something like ArchViz. And it's also, actually, no, that's about it. Okay, so next up, okay, right. So once again, just to reiterate, the general idea behind dielectrics is that you don't get much specular from them, and you get a lot of specular from metals. And I have demonstrated why that isn't always true. This is technically a conductor with a very weak specular reflection, and this is instead a metal with that you can see through. Okay, so next up, I don't actually know what that is. Okay, can you go next one? Okay. Okay, let's now talk about materials that break Fresnel's equation. And this seems weird because the Fresnel equations are this like really baseline thing, but it doesn't actually account for all materials. And this is one of them. This is an enhanced reflector film. So it's primarily used in things like displays once again. And it is a dielectric. It's layered. It is like just layers of a dielectric, but it looks kind of like metal. And in fact, it reflects subtly more than a mirror would. So a mirror is just some silver. This reflects more. So obviously, it's relatively niche. I'll just try my best to compare it against aluminum foil as well. Oh no. That wasn't supposed to happen. Okay, well, there's now aluminum foil on my enhanced reflector film. And it's just stuck on there. Great. It could have happened in transportation, wouldn't be able to show it at all, I guess, then. Oh. Whatever, gonna pick that up later. So we can do a very weird test. We essentially just try to get a, okay. It's just stuck to everything now. Okay. Right. Just again figure out how to get that into a tube. Essentially, I'll just like have light interreflect a bunch, and this should be a decent visualization of the increased reflection abilities. As you can see, this one is almost like glowing. If you look inside, it is okay. It looks very scuffed actually. Anyway, I won't be able to use this reflector film at all anymore because it's just stuck to itself. So there goes my demo, I guess. Okay, so next up, let's talk about rendering it. So what are some of its properties? So first off, it breaks Bruce's law, and it reflects more than 98% of incident light. For reference, actually, I'm not going to be able to give you a reference that quickly. I actually forgot. But silver is reflects significantly less light. It is birefringent, and it's used in display backlights. So if you have a backlit screen and whatever your primary device is, the reason why it's able to shine so brightly is an enhanced reflector film. Once again, pretty niche material. So let's talk about how we could render it. And the general process looks like ignoring the laws of physics and just setting the index of refraction really, really, really high. So in here, if I just okay, what is going on? Okay, okay. So that is 10,000 IOR. For reference, I guess you would never really set this higher than like 2 or 3 for like diamonds or something, and that's just like 10,000. It doesn't make any sense. Light moves so slowly apparently in this virtual material that I guess I don't know, sound could catch up to it or something. I don't know. All right. Let's talk about how some materials don't really look alike under identical conditions. So first off, let's talk about the most simple example, and it is fluorescence and similar effects. Okay, so this is an infrared light detector. There is no infrared, so you don't see anything. But I actually do have an infrared flashlight, and it is this one. If I shine it onto here, and I'll probably once again going to want to stream that. Okay. So infrared flashlight, you can't really see it properly, but if I shine it out the camera, you can see a little bit of it. And if I shine it, can I line it up a little bit better? If I shine it on the metal, there's absolutely nothing. But as it starts shining onto this thing, we see a green light. The very interesting property of this exact material is that it happens to just precisely double the frequency of a light that falls within a very, very, very small part of infrared light. And it just translates that to green, essentially. Okay, so could we render that? Yes, 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 we can. And okay, I've stolen my cursor. Okay. So the way you do this is in cycles is just light linking. You just set the light to only illuminate certain things. But that's not really accurate because we're not in reality, the light could bounce around a lot, and only it can change its properties slightly. And then, when it finally reflects, it might not look that exact way. Ideally, we need some sort of spectral rendering, which could simulate all of this properly. All right, next up. This is a counterexample. This is something that's completely opaque in the visible spectrum, but actually we can use it to make a makeshift IR camera, which is putting it on top of the camera. It can see in infrared light. Okay, it's very dim. Okay, I should probably use the flashlight. This one, okay. So we can see absolutely nothing except this infrared flashlight. Okay. Once again, need a spectral renderer to render that. Before I get into the cream of the crop, let's quickly talk about metamerism, actually. So the general idea is that when we have two different materials that have slightly different, which have slightly different reflectance, spectra, essentially when we put them in a certain lighting condition, they may look identical, but once those conditions diverge, we're going to be able to tell the difference between them. So I have a dedicated color checker, a small one somewhere here. Okay, turn that on. I don't know. Wait, this. So this just has two pigments. So if you see no stripes at the top part here, gonna take my phone. If you see no stripes at the top part, that means your color is relatively white balanced. If you do, that means you need to change it. And as you can see, as the color shifts around a little bit, we can start seeing it pop in and out of place. It's quite subtle. This is used for calibrating cameras. So this it's important to remember that something like this can happen when you're, for example, pick, I don't know, car paints or something. Because in the photos, they generally use, studio lights, which are, LEDs or whatnot, right? They're really powerful. They have 3 distinct components. And once you put them outside, you get a much broader spectrum, which may make it look very different. Okay, so let's talk about the cream of the crop, what really started me on this presentation. And it is RGB. So I think RGB as a general has solved a lot of problems. Okay, it's a great model, right? That's why we use it. But it also has a set of problems with it. And the first one is that imagine yellow light, okay? The way we make it in RGB is we combine green and green and red. But actually, no two colors are created equal. So if we, for example, take a quick look at, I'm actually just going to turn that on. Anyway, so let's quickly look at the ambient light. This is just a spectrometer. It's not like super precise. So say, for example, I pointed at, well, for example, just the screen. We see 3 distinct peaks around blue, green, and, well, we're going to say that's red, even though it doesn't look to be. Anyway, and the outside light, if I just probably just give it a bit more exposure or something like that. No, that's the inverse. Auto. No, can't really properly visualize it. Anyway, so scratch that. The outside light follows a black body spectrum-ish, which makes it extremely wide and extremely desaturated, essentially. So let's quickly take a look at this lamp. It's already sufficiently warmed up, I think, to demonstrate this. If I point it directly onto this, and I'm going to have to point my phone at the spectrum. Okay. Okay. So when I bring it close enough, okay, well, it's not heated up sufficiently, but you can see this one really, really thin peak around yellow, and this is actually the I guess feature of this lamp. It's called a low pressure sodium lamp. The combination of it being low pressure and the sodium lamp makes it have this distinct spectrum, and it has probably one of the weirdest effects that you can ever get. And it is that it tends to desaturate stuff, okay? So right now, you can probably pretty easily see all the different colors in there. It's pretty dark. Just going to shine a light, relatively neutral one. Right, there's all sorts of lights. Right, as I put this in, they all just kind of tend towards this like monochromatic yellow. It looks really uncanny, but it actually happens with a lot of real-world light sources. And I'm going to talk about that a bit later. Right now, I do want to show some other spectras. So, for example, this is a special type of lamp, which inside there's some sort of black light, and it shines onto phosphorus or something like that. So as a result, we get a yellowish light. We can actually see a bit of a concerning peak around ultraviolet light over there. I guess I probably shouldn't have this on for too long then. We can also verify our theory by just shining black light on it. It's, we see it glowing yellow and yellow a little bit. Okay, next up. Right, I wanted to show some more spectrums. Right, so this is an LED lamp. It has a pretty distinct, two very distinct peaks around yellow and blue, and this is a special hue controllable lamp, which also has the same spectrum. Actually, it's a bit more natural, I guess. Finally, I would like to quickly point it at my screen, which I actually don't think I can do. It's a bit far away. Okay. All right. What is our next demo? Okay. Right. So let's talk about how we can emulate this. The most obvious answer is just do spectral rendering. Just integrate over the wavelength, and you will get this effect. Okay, can I stop stealing my cursor, please? Thank you. So this is a scene rendered in Octane. You can download a special build of Blender with Octane for free. Also LuxCore render, which does have some special features, although I couldn't get it to work particularly well, and the workflow is mediocre at best. Anyway, so just quickly go into shading here. Okay. So in here, I have 3 different setups. Actually, no, I don't. That's because it's for light nodes, lights. Okay, so what we're looking at right now is a relatively white spectrum. Okay, can you render though? Okay, relatively white spectrum of the same wavelength that the low pressure sodium lamp has. So let's quickly look at what plopping the wavelength into an RGB formula gets us. It gets us. No, actually, no, wait, this is spectral, because it starts from 1 for whatever reason. So that one that we were looking at was actually RGB. This one is actually an emulation of this exact light. And finally, we have the third input. Why does it start from 1? I just increased the width of the spectrum. We get this weird greenish tint. Looks a bit odd. Okay. So can we do this? Okay, wait, hold on. Before that, what exactly is going on here? Well, essentially, there are no like RGB textures. Everything is our cameras or displays. Everything is so tied to RGB that you really can't escape it. It is everywhere. You can't get a spectral texture, which is what I'm getting to. So what most commercial renderers that use spectral rendering, like Octane, do is that they just emulate the spectrum from the RGB. It's a pretty dirty approximation, all things considered, but it works out in a lot of cases. And it just does a spectral rendering thing. Okay, but if it's just getting spectral data, from RGB, and our scene is so simple, we can also just do the same in cycles, albeit with some extra steps. So first off, we make sure our light does not have a color, and excuse me. Okay, so just make everything white. Then make sure you have your rendering to OpenEXR multilayer. Just render, save. Don't have time for that. Okay, so then I have made a Rust script, ideally Python. Normally I would use Python because there's a bunch of color libraries. This time it actually ended up being a bit too slow for that. So obviously Rust helped out here a bunch. So inside I just pass in the prefix from which it gets the color, the actual EXR, and some data about the spectrum, the mean, the width, and an ad hoc multiplier. I should quickly mention that what Blender calls the EXR multilayer isn't actually multilayer. So you can just check with the EXR info. This is what Blender gives us. It's actually one layer, but it has 17 channels. So just something to keep in mind if you're parsing it. Also, do remember that they are sorted by name, so which is why you get A, B, G, R, even though that really doesn't make that much sense. Okay, so as the output, we get an image. I'm going to quickly find that. Okay, there we go. So you get an attenuated result. This is how it looks like. This is just the attenuated lighting. So then we just go into compositing. Gotta make sure we're in the right scene. There we go. So we load the image. We just add the direct and indirect together. We don't really care about that separation. And we multiply by color. We multiply this attenuated image with our lighting. And we just plug that into the output, and congratulations, we have successfully emulated that desaturation. Is it practical? Probably not. Mostly because it's not really integrated well. So you essentially have to render out an image for each light source, pass in all the relevant information to the script, and then finally you can get a single output, which you then need to add. It's not practical. What could be improved here is integration, obviously, but at some point, you're going to stop making an addition to cycles, and at some point, you're just going to start making a pseudo-spectral renderer. So, I don't know, cycles rework. Okay, do I have anything else? Okay, no, I'm also a bit short in time. Okay, so I'm going to get kicked out pretty soon, but until then, I'm leaving all of this here for as long as I can, and if you want to, you can come up, play around. If you didn't get a good look at something, feel free to just look, just do whatever you want. I'm going to get kicked out, and then I'm going to have to clean it all up. Anyway, I want to thank you all for coming and listening to me drone on about rendering. Thank you.